Hey guys, welcome to the second part of our inclines here. Now we're basically doing two objects with an incline or modified Atwood's machine again. And here's how we approach some of these kinds of questions. So first thing, we're assuming the incline is frictionless, and we have to determine two things: the acceleration of the masses. We remember because they're connected, they'll both accelerate at the same rate. And then we have to figure out what the tension in the rope was. And so previously, when we looked at this, it was pretty straightforward to see which way they would accelerate. But in these questions, we have a different, something kind of different happens here. For my M1, if I'm looking at how my free body diagram is set up for him, M1 has just force of gravity, M1G pointing down, and tension pointing up. Well, M2, I'm kind of sketching off to the side here, but remember he's sitting at an angle. I have M2G pointing straight down. I have FG parallel to the ramp pointing this way, and FG perpendicular pointing that way. And then I have the tension that's connected to that mass pointing up the ramp, and then I have my normal force pointing off to the side here. And so the first thing I kind of have to do is I have to figure out which way the acceleration works. And so that's kind of my question down here. Which direction do they accelerate? And so earlier, the bigger one always won. When an inclined plane is involved, this is not always the case because of the mass on an incline. So what we're looking at is two forces. I'll highlight a couple things here. What we're looking at is the weight of the hanging mass and the component of the weight pointing down the ramp. So what we're looking at is basically who wins between M1G, oops, wrong marker here, M1G, and the FG parallel side. And let's throw the numbers in here that we have. So for the hanging mass, the thing on the left, we're calling that force 1. Looks like the mass is 4. So 4 times 9.8. And we get about 39.2 newtons. For the other one, we have, I think it's 6 kilograms, 9.8. And it's the parallel component, or we go sine 30, and we get a value of 29.4 newtons. So looking at that, obviously that wins. So what that tells us is mass 1, the hanging mass, accelerates down, and mass 2 accelerates up the ramp. So it's going to be important in terms of how we start defining things. So here my question again. It looks like this thing accelerates downward this way, and the block accelerates up the ramp. And so that's going to be nice for me to say. I can actually unfold this. We'll use the unfolding method here. So it looks something like this. We're just using the things that are parallel to the ramp and vertical on M1 and M2, so we might have to take a look at this in class to make sure we understand what's going on here. But these are really the only forces that are involved when the thing is moving. So we can see here the forces cancel, the T's cancel here. So I'm left with negative M1G pointing that way, plus the FG parallel pointing to the right, equals the total mass times the acceleration. That's probably the quickest way to attack these. The hard part is going to be figuring out which way it's accelerating, comparing the things, of course. Plugging in some of the numbers. So M1, that's negative 4. So all we're doing is going to start crunching some numbers. Mass 2 is 6, 9.8. And it is opposite the angle, so it's going to be sine of 30 equals the total mass. We have 10 times A. And when we crunch our numbers, we get a value of negative 0.98, really close to 1 meters per second squared. And I'm getting negative because remember, it looks like everything is going this way in the acceleration vector, right? So, and that was the negative direction, the way we've been defining things. Remember, M1 is accelerating downward, and mass 2 is accelerating up the ramp. So if we start asking specifics about what each individual mass is doing, that's how you would answer that. All right. The other thing is then to figure out what the tension in the cord is, and that is very similar to what we've already been doing. I will look at the free body diagram for mass 1 to analyze that, and it looks like it is accelerating downward. So I can just say T is going up minus M1G pointing down equals, I'm going to write it this way, it makes it look funny, but I think it makes sense. M times negative A, it's telling me it's pointing down. And I think from here, we know how to crunch this number pretty good. When we plug all that in, we should get a value of about 35 newtons. Check my math on that and make sure I'm right. But that is how you approach these frictionless incline problems. So now let's tackle one with the friction. And so in the name of physics, we have a monkey attached to a sleeping sheep on a ramp. And then as we all know, the coefficient of friction for a sleeping sheep on a ramp is exactly 0.15. Determine the following: the acceleration of the system and the tension in the rope. So the first thing we have to figure out is which one is the winner. So here's our free body diagram of the two objects. So notice on this one, the red friction force, that's kind of the new thing going on. I'm assuming it's being pulled up the ramp, so friction has to point down. We have to figure out which one is the winner, and so in order to figure out which one the winner or loser, we're looking at the M1G versus the FG parallel to see which one works. So plugging in some numbers, the monkey is 24 kilograms times 9.8. And the sheep is a 28 kilogram sheep times 9.8 times the opposite value here, so sine of 40, and we get 235.2 newtons versus 176.4. So it looks like the adorable monkey wins, so the monkey will accelerate down and the adorable sheep will accelerate up the ramp. So the first things we got to do is we have to look at what we have. We know we're going to have to figure out what the friction force. So let's go ahead and figure out what the friction force is. Friction force is mu times the normal force. Remember, the normal force is equal to the perpendicular chunk here. So the normal force is equal to mg cosine theta, if I were looking at it this way. So over here, I have mu times mg cosine theta. Plug in all my numbers, 0.15. Mass of the sheep, 28 kilograms, and cosine of 40. This gives me a value of about 31.5 newtons for the friction force. And it looks like I have all the information that I'm going to need here. Look at my net force equation, unfolding it again. So I have negative M1G. I'm going to call, once again, down negative, up the ramp negative, and the ramp positive, and I think that'll make sense. Negative M1G pointing that way. I'm going to add the FG parallel to this. I'm also going to subtract friction. I'm sorry, not subtract, add friction. It's pointing in that same direction. So adding friction going down that positive way. And then look at the total mass times the acceleration of the system. Plugging everything in looks something like this. And then when you crunch the numbers, we should get an acceleration value of about 0.525 meters per second squared. Once again, monkey is going down, and the sheep is accelerating up the ramp. Now, in order to find the tension, we kind of do the same thing we did a second ago. Look at free body diagram number 1, or for mass number 1. We have tension going up. We have the weight going down. And it's going to be negative m1a simply because it's pointing down. We have all of our numbers. We can plug everything in like so. We could factor if we wanted to even, might make it a little more straightforward. G minus A. So when we get our tension, we have our mass of 24, gravity is 9.8, and the acceleration at about 0.525. So when we crunch our numbers, we get 24 times 9.8 minus 0.525. We get a tension of about 222.6 newtons in the string connecting the adorable monkey and the even more adorable sheep. So let me know how that goes, and I'll talk to you guys tomorrow. Okay, thanks, bye.